talking about today first law of thermodynamics. Now we have discussed this yesterday, but there are few important things I would like to highlight them again. One is that when we are talking about this law, we are talking about a closed system, okay, which means there is no flow of mass into or out of the system. The second thing, this equation which is written here is written for a cycle. These following 4 or 5 equations, they are written for a cycle, which means the system comes back to its original state. Okay. Then we talk about net amount of work done by the system on the surrounding. Okay. So system is working on the surrounding. That means we are getting the work out of the system, because that was initially the objective of making a machine. When when thermodynamics started, that was the time when the machines were being used, or thermal engines were being used to produce mechanical power so that they can run the factories. For example, steam engine, you use heat power to run the locomotive, or your IC engine you use to run a vehicle, and of course you can run a pump also with that and all those things. So what you are doing is basically you are converting heat energy or thermal energy into work. So the work was objective. So that is why people call the work done by the system on the surrounding as positive. So this is only a nomenclature. If you want, you can write it otherwise also the work done on the system is positive. There are certain formulations in other branches. It makes no difference. There also first law is being taught, and you can say that work done on the system is positive. That also you can say. It really makes no difference. It's a convention that the right side will be positive, the left side will be negative. You could have done it otherwise also. Okay, so here net work done by the system on the surrounding, and net means the work can be done in both the direction, and we are finding the sum of that. Net the gain. Similarly, the net amount of heat given to the system by the surrounding. And so our objective was we were supplying energy to the system, thermal energy, and in return we were getting the work. So we took thermal energy given to the system as positive, work done by the system as positive. And as I said, you could have reversed the sign. There is no problem. We could have done it. So this is the statement of the first law of thermodynamics. Okay, the briefest or the smallest statement which contains everything. Okay, but then we have to enlarge upon this to understand it in a better way. And then I put these equations. I will not touch them again here. Just give you some example. We have discussed this example yesterday, but we were doing it in hurry. But now I am taking it up in some more detail. Now you can think this as your system. I have made it just like a reservoir, but a tank where something is going in and something is coming out. You take it as a system or a closed system, even closed system, because what is entering in is not water here. What is entering in is energy. Q1 and W1. These are entering in. What is coming out is also energy, Q2 and W2. So in a closed system, energy can go in and come out. So this is a closed system. Now, what are the conclusions we draw from the first law statement? What is happening is the amount of heat given to the system or the work done on the system. So whatever energy you are giving to the system, it goes inside and stored there. It is not necessary to bring it out. E1 and E2 are independent. You can only give in the energy or you can only withdraw the energy. Anything you can do, whatever combination you do. But what happens that whenever you are giving energy, it is stored within the system. Okay. So whether you do heat, give heat or work, it is stored within. And what is the result? It increases the net amount of energy inside the system. So this E, this, or you can say the internal energy get increased. Okay. And same thing happens when you draw the energy from the system. So net amount of heat removed from the system or work done by the system, E2 comes out of the energy stored in the system. So what you are giving in is stored within the system. What you are withdrawing is actually coming from a storage. Okay? And that is internal energy. Now your E2 can be greater than E1. You can give in more, withdraw more. Sorry, you can give in less and withdraw more. What does that mean? There is something already inside from where you are withdrawing. Okay. So there is already something in the reservoir. Okay. And whatever is the excess you are getting is actually coming from the what is stored in the system. Okay. Now, if the system comes back to its original state, is something like a tank which is filled up to a level, top of the tank, you put some water, you draw some water, and actually it, after the cycle it comes back to the same state. What does that mean? The amount of mass water put in is equal to the amount of water which you have drawn. So same thing here. If the system has come back to its original state, it means that amount of energy given in is equal to the amount of energy withdrawn. So this is what the first law is. Okay. Which you can also say that the energy is conserved. Right. So temporarily you can get more energy. Temporarily there may be a loss of energy, but when you are going in cycle, nothing is created and nothing is lost. And this is the first law, is law of conservation of energy. Okay. Now there are certain important points here. Of course, what I said before is also important. And these, when you are applying this law, the system must move in integral number of cycles. Only for this statement, it is not necessary. I will talk about it. When we are applying first law, it is not necessary that the system should be closed. It is not necessary that the system should come back to its original state. No, we have equations for all the cases. Only the statement which is there it is mentioned like that. Okay. And next we then will expand it. We will find that we can bypass those restrictions. Okay. So system must move in integral number of cycle, and it says the work and heat are taken proportional. Now this proportionality is there because the units are different. One is measured in calorie, the other is measured in joules. If you have the same unit, then there is no need of proportionality. Also, the amount of work done is equal to the amount of energy given. You need not put a proportionality constant there. Okay. So this is the first law statement. Now another thing is that validity of first law. How does this come about? What is the origin of this law? Now, one thing you must understand, the first law is only a law and it is not inviolable. It's not that it cannot be violated. There is no such proof that first law cannot be violated. No such proof is available. Then why do we believe it? Because this law is actually a representation of experience gathered over a century by the scientist. It's basically all your experience which the scientists gained over the centuries of experiment, it is summed up into a statement. Are you getting? So the scientists were always trying that somehow we make a machine which can work without petrol or without electricity or without any energy. This was the objective, and a very high objective, impressive one. If that would be the case, there was no need for you to come to the class. Sleep easily in your room. Energy is freely available. But then there is a restriction that energy cannot be created. So for producing work, you require energy. So when they found that they have not been able to produce or develop any engine which can work without heat being given to it, then they said, enough of it. Now let us put a law that energy can neither be created nor be destroyed. So there is no proof. The only thing is, nobody has so far found an experiment which says that energy can be created or energy can be destroyed. Nobody has been able to do that. So long nobody is able to do it, we jolly well continue like that, assuming this law and applying it for our day-to-day problems. Okay, so the only sanctity of this law is that it has not been violated so far. So your choice. So the thing is, why it is valid, what is the sanctity of it, that it has not been violated so far. Okay, but then we already know, then Einstein came and he said E is equal to mc square. Mass can be, and obviously at that time the law of energy was broken. So people rephrased it, said mass plus energy is conserved. Because there is a one-to-one relationship between mass and energy. So ultimately, science is not telling you something new. आपको लगता है कि साइंस बहुत वंडर है. Science is not telling you anything new. It is only summing up your experience into certain statements which you can use again for, you can say, your own benefit. So this is what actually happening. Okay. So this is as far as the first law is concerned. If you have any question. Okay. There is one thing more I would add to here, other than this law, that what nature has done is it has put constraint on us. You'll find that everywhere, we have talked about right in the beginning, freedom. But we will find that there is no freedom. At many places, nature has put boundaries for us. One of this boundary, that you cannot violate the law of energy. Then there are other boundaries also. You cannot go back in time. You cannot fly, or you cannot live without air. So many things, so many restrictions are there. And why nature is doing it? Because it is driving you in a particular direction. It is forcing you to move in a direction. आपको पता है घोड़े के मुंह के ऊपर ब्लिंकर्स लगाए जाते हैं. They are called blinkers. What do they do? The horse cannot see sideways, so it runs only straight. So they are sort of blinkers put by nature on humanity. You have to go in this direction. It is forcing us to do the work and in the process grow. So the underlying principle, more than the law of energy and the more than the law of entropy, is to grow. Right? And because nobody can measure growth, the real growth of human beings, that is why we don't have any law for that. We can only say the evolution is continuing, evolution is happening. Right? What is evolution? Evolution is growth. And why this evolution has come about? Because nature forced you to earn food for yourself, to earn living for yourself, and in the process put some constraints, and in that struggle you started evolving. This is how the animals evolved. And even the current situation is that evolution is continuing. You might have felt that evolution to ho hi nahi raha hai. But the scientific statement is that evolution is still going on. But the evolution is going now at the mental level. So outside in the body there is not much change, or the change is very small. The change is happening in the mind. And this is not my statement. This is scientists are saying this. So that evolution is continuing. So this is the play actually which is happening. And the part of it is the conservation of energy principle. Okay? Many of our work will stop if we do not have this constraint. If energy is freely available, many things will stop. Our efforts, things will be there, but our efforts will be stopped. And consequently, our growth will stop. So what nature wants from us is to grow, right? And if we accept that principle, then it will remove the constraints. It is only when we are not ready to grow, more and more constraints are put on us. Okay, so this is how it goes about, but just a digression. Okay, coming back to the first law, there are certain corollaries of first law, and this is something you can say extension. So from that original statement, we will proceed and will form different statements from this. The first corollary is existence of a property called internal energy. We have been using this word before, but it is here for the first time that the internal energy is acknowledged, and it is seen that there is something like this. Okay. So what it says, first law we already know, there is a closed system internal and okay. There exists a property of a closed system, let us name it internal energy, such that the change in its value is equal to the difference between the net heat supplied to the system by the surrounding and net work done by the system on the surrounding as system moves from one state to another. So we have now moved from the restriction of cycle to state 1 to state 2. Okay. So what this corollary is saying, when you move from state 1 to state 2, in the process you give some heat to the system, some work is done by the system, and if you add up the two, total amount of heat minus the work done, so that will be the net input to the system. So the change in value of, so there is something, as we saw in the previous example figure box. So there is something in the system which stores the energy. And what is that energy? That is internal energy. So whatever you are giving in is stored as an internal energy and which can be subsequently used. So it's saying that there exists a property called internal energy such that change in its value is equal to the net amount of heat given minus the net amount of work done by the system. Okay. Now, what is the definition of a property? We have talked about it right in the beginning. And we said the property is any parameter which is of interest to us and its value, change in its value is independent of the path. So now we have to prove that internal energy is a property. Whatever path system follows, the change in value of internal energy will be same. It will be independent of the path. If there is any parameter which is independent of the path, it can be called a property. And we are saying internal energy is a property. So if internal energy is a property, we have to prove that it is independent of the path. So now what we do, we draw these three paths and you will find that A and B are forward, you are moving from 1 to 2 and C is backward. So A plus C is a cycle and B plus C is also a cycle. Agreed? If you add A and B path, it becomes A and C path, it becomes a cycle. If you add B plus C path, it becomes a cycle. Now, what it is saying, if you are moving in a cycle, the statement of the first law says the amount of heat given, this is the heat given. Heat given on path A is sigma del Q A 1 to 2. Heat given on path C is delta QC 1 to 2 minus the work done on path A minus the work done on path C. They should be equal to 0. This is the statement of the first law. And similarly, you take path B and C, cycle BC. So heat given on path B plus heat given on path C minus the work done on path B and minus the work done on path C will be equal to 0. And if you use these two equations, you can subtract terms of heat and work along path C and you will get this equation. So don't fall into mathematically proving it, it is proved. There is no problem. Simple, you can see it later on. At the moment, focus on the concept what I am telling you. Okay. Mathematics you need not bother. It is too simple. You can do it yourself later on. Okay. So what do you get here? If you add these two equations, you will get heat given on path A and minus the heat given on path B, and this is the work done by the system, and okay, minus of this total, this will be equal to 0. And you can rearrange that, and what you will get this. That difference between this del Q minus del W along path A from 1 to 2 will be equal to del Q minus del W along path B 1 to 2. So here it is a term, a quantity which is independent of the path. When you are moving from state 1 to state 2, either by path A or either by path B, your difference will between the two remain same. And then we can say that this is nothing but U. So this is equal to change in internal energy along path A when the system is moving from 1 to 2, and this is equal to change in internal energy along path B as the system moves from 1 to 2. And in both the case, this is same. So U on path A and U on path B, change in the two, change in energy in along path A and change in energy along path B is same. So U is called internal energy. So you can say that it is internal. So what has happened that we know what is internal energy, okay? And here you will find that by this you can find what is the change in internal energy, but you cannot find what is actually internal energy. So U1 is not known to you, U2 is not known to, but U2 minus U1 U2 minus U1, sorry, that you know, that is equal to delta Q minus delta W, and of course sigma you can do 1 to 2. So the first law is saying that there is something, some property, some quantity, change in its value is equal to, you can find del Q minus del W ka integral, but what is it actually you don't know. So in thermodynamics we never know what is the actual internal energy in the system. We don't know. We only know what is the change in internal energy. Okay. So this is called the equation of first law. You can also see this is the equation of the first law. The equation is, this equation is valid only for closed system. For open system, a separate equation is developed. So that we'll do about 2 or 3 lectures down the line. What is the equation of first law for open system? Currently we are talking about only closed system. Okay. So this is first corollary says that there exists a property called internal energy and whose value can be found out by summation of delta Q minus delta W. Okay. Then it says the law of conservation of energy. We say the law of first law is same as the law of conservation of energy. How come? Now you see that if a system is isolated, Q will be equal to 0, W will be equal to 0. No energy can be transferred in, no energy can be removed out of. Then delta U will be equal to 0. So for a closed and isolated system, closed and isolated. Q and W are equal to 0, which means delta U is equal to 0. That means if a system is isolated from the surrounding, its internal energy is conserved. It remains same, U1 equal to U2. This is how the law of conservation of energy has come in. Okay. Then there is another corollary which says perpetual motion machine of first kind is impossible. Now we have already talked about it briefly. The statement says, in fact, importance of this statement is, this is another way of putting the first law, but it was more close to the experience and the objective of making a machine which is producing work without consuming energy. When people failed in that, what they said, it is impossible to construct a machine that will operate in a cycle and produce net amount of work done without receiving any net amount of energy from the surrounding. So if you apply that equation, if you are moving, so first condition is that operate in a cycle. If you are operating in a cycle, delta U is equal to 0, which means Q is equal to W. Now you have said that Q is equal to 0, we will not give any heat, so you will not get any work. So if your machine is moving in a cycle, you can have a machine without giving the energy which will do work for you, but for time being. For time being. But if you want to reuse that machine, you want it to run in a cycle, then it is not possible. You will have, if you Q is W 0, then W is also 0. Okay. So you can say it is impossible to construct a machine which will operate in a cycle such that it will produce net amount of work without net amount of heat being given to it. ठीक है, तो ये एक और corollary है. This is also, you can say, the law of conservation of energy in a way. Okay. Then we will talk about further extension of first law, and we will write different type of equations to apply, to use first law. Okay. Now, one modification I am doing, that I am adding the macroscopic energies in it. Right? And currently we are talking about integral forms of equations in integral form. So, which means that we are applying equation between state 1 to 2, time t1 to t2. There is a finite difference between the two states, 1 and 2, time t1 and t2, and we are applying the equation between state 1 and 2. Okay, and we are talking about whole system. So this is the integral form, that we are talking about the whole thing. We can talk about differential form where we can apply first law to a very small quantity, part of a system. We can apply first law to part of the path. Okay. part of the time movement. In a very small part we can do. Because first law applies whatever the condition is, whether you are talking about a very small component or very large system, whether you are talking about a part of a path or the whole path, or whether you are talking about a small change or the whole change time wise, it applies there. So currently the equation we are writing between state 1 and state 2, and we have made one modification that there are two ways we can write this. One is when we are talking about stationary system. When you are talking about stationary system, there will not be any internal energy and potential energy. Then the equation will be same, Q minus W is equal to delta U. But when you are talking about potential and kinetic energy of a system as a whole, macroscopic kinetic energy and potential energy, then equation will be modified as Q minus W is equal to delta E. Okay, so both these forms are possible, available. Here the other energies, the macroscopic energies are also coming into play, and in the next equation these are not there. Okay. Now the same equation we can divide by mass of the system. If we divide by the mass of the system, what happens? Because mass is constant, is a closed system, so left and right the mass is same. You can divide the whole equation by mass, your equation will become like this: heat per unit mass, work per unit mass, and change in total energy per unit mass. Heat given per unit mass, work done per unit mass of the system, and change in energy per unit mass of the system. This becomes specific. So specific means per unit mass. So you can write equation like this also, because both side mass is same. And okay, we will stop here because I have to take attendance also. This will continue. So we will see. I'll just show you then in terms of rate, when you divide by time, what will happen. Then in terms of specific parameter and rate, both. You can divide by both mass and times together. For a cyclic system, what will be the equation? Then first law equation in a differential form, which means you are only talking about a small mass, small movement, and small time change in time. That also you can do, and you can write equations in different differential forms also. Okay, so many different forms. Only thing is that you understand them. You cannot remember all of them. If you want to remember, it will be difficult. If you understand them, it is very easy. Okay, there are 15 equations I will be giving you, but you have to remember just one. And in a different form, you write it down. So better understand it instead of just remembering everything. It will be difficult.